In this video, we look at spin-orbit coupling, a magnetic effect within an atom. Take an electron with non-zero orbital angular momentum, L larger 0. You can picture it orbiting around the nucleus in a defined sense, for example counterclockwise. This is the nucleus with a charge of plus c. This is the orbit of the electron. And the electron orbits counterclockwise. Now, let's change the reference frame. Imagine you are the electron. Then you will perceive the nucleus rotating around you. If you imagine the electron is the Earth and the nucleus is the Sun, you'll perceive the Sun rotating around the Earth, even though it is the Earth that rotates around the Sun. Now, the nucleus is positively charged, so from the point of view of the electron, there's a positive electric current flowing around it in a loop. Like any circular current, this current gives rise to a magnetic field, as seen from the reference frame of the electron. The field lines look like this. The magnetic field is proportional to the orbital angular momentum of the electron, L. The higher L, the higher the magnetic field. In general, any particle moving in an electric field experiences a magnetic field. The electron itself is spinning and has a magnetic dipole moment. You can regard it as a tiny spinning bar magnet. Here's the spin angular momentum vector, S. And here's the magnetic moment vector, mu, S. They're antiparallel. The electron spin magnetic moment feels the magnetic field from the nucleus. Its energy will depend on how it is oriented relative to this field. Therefore, the spin and the orbital angular momentum of the electron interact, although not directly, but via the presence of a charged nucleus. This is the spin-orbit coupling. To account for this coupling, we have to add an extra term to the Hamiltonian. The overall Hamiltonian is H0, which is the familiar Hamiltonian with the familiar kinetic and electrostatic energy terms, plus HSOC, the spin-orbit coupling Hamiltonian. This Hamiltonian is new and is given by the interaction energy between the electric field to the nucleus experienced by the electron, dot product with the spin magnetic moment of the electron. And if you simplify this, you'll get some coefficient psi of r times L vector operator dot product S vector operator. Basically, we have a dot product between the orbital angular momentum and the spin angular momentum. The prefactor psi is equal to z e squared divided by 8 pi epsilon 0 me squared c squared times 1 over r cubed. If you compute the expectation value of the spin-orbit Hamiltonian for a given hydrogen wave function, you get the energy contribution due to spin-orbit coupling. It turns out that this energy contribution, E, SOC, is proportional to z to the fourth, to the nuclear charge raised to the fourth power. Therefore, even though the spin-orbit coupling is almost negligibly small for hydrogen, it is of dominating importance for heavy nuclei further down the periodic table. Let's illustrate the spin-orbit coupling with a simple picture. Here's the nucleus, and an electron orbiting around it. Let's have a spin-up state for the electron. So this is the spin angular momentum vector S. It points up. If the electron rotates counterclockwise, its orbital angular momentum vector points up as well. We draw it at the position of the nucleus. The two angular momenta are parallel, so the dot product in the spin-orbit Hamiltonian is positive, and the energy contribution is positive as well. This relative orientation has high energy. On the other hand, let's look at the spin-down state in the same orbital situation. Now, the two angular momenta are antiparallel. The dot product in the spin-orbit Hamiltonian is negative, and we get a negative energy shift, so this state has a low energy. In summary, we have looked at the spin-orbit coupling. It is an energetic contribution due to the interaction between the spin magnetic moment of the electron with the magnetic field it feels as a result of orbiting around the positively charged nucleus. The spin-orbit coupling goes with the fourth power of the nuclear charge.